Logic gates are the reason why you are able to watch this video and do anything regarding electronics that requires computing, like your phone. Logic gates are really not that difficult to understand, especially today, because my genius will explain everything there is to know about them. Let's begin. Logic gates perform Boolean functions, which just means that logic gates read and output either a high or a low signal. Logic gates stem from transistors. This is because transistors are electrical switches and they can be manipulated to send certain signals with whatever input. Let me show you. In this circuit, you can see two resistors and one NPN transistor. They form what we call a NOT gate, or an inverter. The resistor connected to the base is in charge of limiting current. This just protects the transistor from damage. The second resistor that goes to the collector is a pull-up resistor, which prevents a floating state. When you hear floating state, think of a kid that's confused about his or her gender, and the pull-up resistor as a parent that reassures their kid that they are in fact that gender. The pull-up resistor sets a high signal reference when there is no signal. Another important gate is the AND gate. All it does is it reads two inputs, A and B. If both inputs are high, the output will be high, else the output will be low. The resistors connected to the base are the current limiting resistors. They protect the transistor. The resistor connected to ground is a pull down resistor. Same thing just like a pull up resistor, it just sets a low signal reference. Now that you understand NOT and AND gates, you understand all logic. Well, to an extent, because they are the parents of all logical circuits. Because with just those two, you can create everything. But before I can show you this, I do have to tell you a couple more things that fill in some blanks. One would be truth tables. They're just tables that list all the possibilities of inputs and outcomes of a certain logic circuit. For an example, an AND gate, you have two available inputs. This means to see the total of all possibility inputs and outputs, you need to square the total inputs. So 2 squared is 4. So there are 4 possible input patterns with 4 possible outcomes. Do note that the outcomes depend on the type of logic gate that is being used, and all the inputs can never be the same pattern. The second is Boolean algebra. Don't worry, Boolean algebra is simple because it only uses 1 or 0. The letters represent the possible inputs, which is 1 or 0. So if x equals y and x equals 1, then y equals 1. Ooh, I almost forgot. In Boolean algebra, multiplication represents the AND gate. If you see addition, it's the OR gate. If you see an apostrophe, this is the inverter. And later down the road, when you get into more complex gates, you will notice a circle with a plus in it. This is an exclusive OR gate. As you can see, Boolean algebra is simple. There are only 4 mathematical operations. There is no division, subtraction, exponents, or even roots. But remember, parentheses still work as if you were solving a regular algebraic equation. De Morgan's law falls into Boolean algebra. It's a law.
Well, duh.
So, let me just say, it states A plus B naught equals A naught times B naught. It's better if I show you in a simulator because trying to do this in your head will confuse you. So here you go. Alright, this is Digital Logic Simulator created by Sebastian Lake. I think that's how you say it. This is a great application, I'll say that. It's actually pretty damn good. It's very good for simulating logic gates, and it's very simple, and I like it. Simplicity is best. A times B naught, which is basically a NAND gate, is the same as A naught plus B naught, which is an OR gate. So, in order to make an OR gate with an and a NOT gate, it's actually quite simple. Now, the truth table goes, it's exactly like an AND gate, but the opposite, right? So, if an AND gate is on only when it's both on. You will have to reverse it. So that makes it a NAND gate, right? Now, it will only turn on when these two go on, right? But now we just got to make it so that these guys are sending a 1 here. So this one gets turned off. And how you would do that is put these two here and invert these inputs. That means if both of these stay off, this one will go off. But if one goes on, meaning this thing goes off, as you can see, here, let's zoom it out. If any of them go on, the signal shuts it off, closing this gate, inverting this output, so it goes on. Now, the same thing with this side. So that's our OR gate. Now I want to show you a NAND gate. It's exactly like I just showed you, and it just is an AND gate with a NOT at the end. That's all it is. If both go on, the signal goes off. Next will be the NOR gate, which is same thing like a NAND gate, but with the OR gate, output is inverted. So the signal will only go on if it's both off. So if any signal is present, there will be no signal on the output. The NOR gate, the exclusive OR gate is actually pretty fun. How can you create this logic gate? Well, all you gotta do is take the ones that are in the outputs and write the A's and B's out. So here's how you would do it. A times B, which is just these two here. Why is this okay? And the reason why I'm writing this line out is because this one has a 1 in it. Now I'm not going to write out this line because, well, this one has a 0 at the out. So we don't care about that. Now, this here is a 0. So it's basically inverted A. So that means you're going to put an inverted sign on the A. So it's now not A times not B. Same thing goes with this line. This line has a 1, so A is 1, so that's not inverted. B is 0, so B gets inverted. That's an 8. Here we go. Now, all you do is put these two in an OR gate, and voila, you got an exclusive OR gate. So here, let's show this to you. If you have 2 NOTs and AND gate for both of them, and then an OR gate at the end, how you're gonna do is you're gonna, for the first line that had a 1, was A inverted times B, and then the next line goes A times B inverted, and then you put those two into an OR gate, and that gives you your exclusive OR gate. So if both signals are off, nothing's going to go on. If one signal goes on, the output goes on, as you can see. And now if both signals go on, it's going to go off. So that's your exclusive OR gate. The XNOR gate is just like NAND or NOR. The output just gets inverted. And this is the same thing. All of these are the same. So this part here is the exclusive OR, and this is the inverted part, which is here. Which is here. And this is this. So that's your logic gate. And let me show you how you can create your own customized truth table and make a logic circuit out of that. How can you create a customized truth table and then the logic gates to it? Well, obviously you just got to create your own logic table. So I'm just going to create my own right here. So I'm going to go with the standard A, B. And I'm gonna have two outputs. Now you're wondering, what the fuck? You could have two outputs? Yeah, you could have however many inputs or outputs you want. That's the cool part. So I'm gonna say this is out 1, this is out 2, or that's a Z, 2. So, of course, with two inputs, 2 squared is 4. So that means you'll have only 4 possibilities of input patterns. So it's going to be 0, 0, 0, 1, 1, 0, and 1, 1. Now our output is the customizable part. So how do you do this? Well, as I've explained a little bit previously in the XOR gate, you pay attention to the output with a 1, and then you go off of the inputs. So in this output, we have a 1 here, so I'm going to focus on the 2 inputs. So A and B, so it's going to be A times B, and none of them are 1s, so that means I'm going to invert those 2 values. The next line is A and B, but B is 1, so I'm going to invert A because A is 0. So A times B, A is inverted. Now I go on to the next line. So I have zeros here, so I'm going to ignore the outs for this. So this is not going to go to this lamp anymore. 1 here, so that means A times B, B, ugh, I hate the way I write B's, B, and A is 1, B is 0, so B gets inverted. And AB is both 1, so none will get inverted. So A times B is going to light up these 2. So this is going to go to out 2, and this is going to go to light 1, inverted, and it goes to AND gate. So A and B are inverted, so that means if I do not gate here, there we go. That goes to an AND gate. So this is A, it's already inverted here, so we're just going to grab it off of that, and we're going to put this in here. So we're just going to kind of stem off of it. And this one goes here. So what I've just done is B goes to AND gate, and then inverted A goes to an AND gate, and then these 2 get inverted and go to an AND gate. Now at the end I will just put these 2 together into an OR gate, and that will go to my out 1. And now as you can see, both outputs are off, and I get a 1 here. Now if only B goes on, which is this one, it's going to stay on. But if any other pattern happens, it goes off. So if this goes on, it's going to go off. Now I have to create the other portion, which is the output 2. All I gotta do is just do this. And now this goes on if A goes on, or if both of these go on. So you arrived at the end of the video. Thank you for watching, and if you need any more help or you got any questions, don't be afraid to ask. See ya.